When we're working with implicational statements, the if-then statements, we focus mostly on what values from the domain make the statement false. And then we infer from that that the other values in the domain would make the statement true. So it's much easier to think about when an if-then statement is false than it is to think about when it's true. In the first statement, we have if z ends in a 4, then z is divisible by 4. So a statement that would show that's false is a statement that satisfies the first part, the hypothesis, and then fails to satisfy the conclusion. So if you saw that statement and someone claimed that that was always true, you would say, well, no, that's false because of numbers like 14, 34, 54, and so on, all numbers that end in 4 but are not divisible by 4. If you remember in class, we called these counterexamples to the statement. The second statement says if p is prime, then p plus 1 is not a perfect square. That is mostly true. The only value of p for which that's not true is the number 3. So there's not a whole bunch of those. The next two statements, next two problems, we're getting into the difference between an implicational statement and its converse and its contrapositive. We talked about contrapositive shortly in class. We didn't talk about converse. The idea of converse is to just reverse the statement so that the predicate and the hypothesis and the predicate and the conclusion switch roles. The reason that this is a thing, the reason that people study this is because when we do mathematics, we're really starting to study the relationship between two properties, and it's often the case that we don't really know which property should be the hypothesis and which property should be the conclusion. So when we're doing mathematics, we often try the predicates in both roles, and so trying it one way and trying it the other will have a name like converse. So I'm not going to try to write the converse out carefully in English because again it's hard to write on this pad. But the English statement of the converse is written on the back of the worksheet. Generally, in a converse pair would be a statement. If one statement is of the form P implies Q, then the converse is simply the statement Q implies P. So it's just reversing the role of hypothesis and conclusion. That is awful writing. Converse is what that means. So, for example, I'll just say out loud that for the first statement here, if z ends in a 4, then z is divisible by 4 was our original statement. So the converse will be if z is divisible by 4, then z ends in 4. So hopefully you can write that out in words, and then you can analyze that to see if you can find a counterexample for that statement. And there are a lot of them, of course. So statements like, numbers like 8, 12, 16, 20, these are all numbers that are divisible by 4 but don't end in a 4. So they would be those would be counterexamples to the converse statement. The B part, it's a little harder to think about, but of course we think about perfect squares and primes, but the converse will be if p plus 1 is not a perfect square, then p is prime. So we're just switching the role of hypothesis and conclusion. If you write that out first in words and ask yourself what are the counterexamples to that, you'll come up with numbers like 1. 1 plus 1 is not a perfect square, but 1 is not prime. 4 is another counterexample. 4 plus 1 is not a perfect square, and 4 is not prime. And then a few more you can see on the worksheet solutions I wrote out. The first few things that are counterexamples to that statement. The contrapositive we talked about in class. Let me remind you that if you have P implies Q, then the contrapositive is not Q implies not P. This is just reversing the role of hypothesis and conclusion, but negating them both. And the significant thing here is that these are equivalent. These are logically equivalent, these two statements. That is not true for the original statement and its converse. So I'll put not equivalent here. The statement and its converse are not logically related. The statement and its contrapositive always will have the same truth value. So if one of them is true, then the other one has to be true. And so if you write out again in words what the what the converse would say. I'll just say it, and you can read it on the back of the sheet. For the first sentence here, it would say, if z is not divisible by 4, then z doesn't end in a 4. That would be negating both and reversing the order. And if you do that, then the counterexamples to that are 14, 34, 54, and so on. So in other words, what you recognize is that the counterexamples to the original statement up here are exactly the same as the counterexamples to the contrapositive, and that's because of this logical equivalence. And so once you've written the converse of the second statement, which would be if p plus 1 is a perfect square, then p is not prime, you'll find that the only possible counterexample to that is, again, the number 3. So it's not a coincidence that the counterexamples to the contrapositive match the counterexamples to the original statement, again, because those two things are logically equivalent. And then don't forget the converse is logically independent of the original. So there's no logical connection between these two things, and we can see that in the sense that the set of counterexamples for the original are really different from the set of counterexamples for the converse. Okay, so it takes a little experience to recognize the structure of sentences when they're written in English, so this next problem gives you some practice with that. If you're going to the library, so we'll call that P, then I am going to the library, we'll call that Q. So my original statement has the form P implies Q. So let's see if we can recognize what each of these other sentences are structurally in terms of P and Q, and then we can decide what role that has. So the first statement says, if I'm going to the library, that's Q, right? Then you are going to the library, that's P. So it reverses the role of hypothesis as conclusion, so it looks like Q implies P, and so that's the converse. These next two sentences point out something that's important, and that is that people don't always talk the same way. So here we have, I am going to the library if you are. The part after the if is the hypothesis. There's no rule in English that says that part has to be written first. So this really is an if-then statement, but the hypothesis is here. The hypothesis is always what's coming after the if. So again, you are going to the library is P, and I'm going to the library is Q. So the hypothesis here is P and the conclusion is Q. So this is just P implies Q. And so in other words, this is exactly the same as the original statement. So if someone says, if you are going to the library, then I'm going to the library, and you say, I'm going to the library if you are, those two things say exactly the same thing. And so similarly, this next sentence is just the converse of that. Okay, so that one also is the converse. Now we have, if you are not going to the library, so that is not P, then I'm not going to the library, which is not Q. So let me just write that out in symbols. So not P implies not Q. And that is not either one. That is not the converse, and it's not the contrapositive. The hypothesis and conclusion are both negated, but they're not switched. So what we have in part D is it's essentially the contrapositive of the converse, which is a bit of a mouthful. So we have a name for that. We don't use it all that often in math, but it does have a name. That's called the inverse of the original sentence. And so because that is the converse of the contrapositive of the converse, the inverse and the converse are logically equivalent to each other, but neither one is logically equivalent to the original statement. So that's a bit of a trivia. You'll see that mentioned in the book, but that's not something that we'll hang on to the term inverse, because it's not as common in mathematics. You hear converse and contrapositive all the time, but inverse is really just somebody giving a simpler name to a combination of converse and contrapositive. In E, we have you are going to the library, but I'm not going to the library. So that but is an and statement, right? We talked about that. And so in symbols, we would say you are going to the library is P. I am not going to the library is not Q, so I'd have P and not Q. So that's not an implication at all. It's not an if-then statement at all. So it's not going to be a converse or an inverse or a contrapositive or anything. But it is actually the negation of the original sentence. Right? This is exactly what would have to happen for the original sentence to be a lie. remember, if the original sentence says, if you were going to the library, then I am, then for that to be a lie, it would take you going to the library and me not. So in other words, P and not Q has to happen in order for the original to be a lie. So E is not any of those things that I listed, converse, inverse, or contrapositive, but it actually is related to the original statement. It's the negation of the original statement. Let's see, F says you are not going to the library if I am not going to the library. So here again, this is my hypothesis, the words after the if. So that's I am not going, so that is not Q. And then you are not going, so that's not P. And so that's our contrapositive. And then finally, part G says we are both going to the library. That's just P and Q. And again, that's not an implication, so it's not logically connected to converse, inverse, or contrapositive, and it's not it's not anything. I'll run through one of the truth table problems. I won't do both of them, just to save time here. So maybe we'll do the second problem. This truth table has a little bit more complexity than the first one, so I'll do this one as an example and you can check the other one. We see that we have an AND statement that we're trying to build a truth table for, and so I think to myself, well, I can build a truth table for this AND statement if I know the truth values of the two pieces of that. So I'll add columns, one for P or R, and another for P implies Q. And I know that if I can build truth tables for these two guys, then I can put those together with a logical AND. So now I back up and look at this. I have an OR statement, so I know I can build this OR as long as I have previously a column for P and a column for R, which I do. And I can build a table for P implies Q if I have a table for P and a table for Q, which I do. So I'm ready to get started. I do need to put in my initial values, and I wish I had put these in now. It's hard to write these little boxes, but I'll start off with 4 T's and 4 F's in my P column. And then in my Q column, I'll alternate 2 T's, 2 F's, 2 T's, 2 F's. And then in my R column, I'll just alternate true and false. So if I kind of have that idea of filling in half trues and half falses sort of over and over again, then eventually I'll get all of my pieces in there. So I always label those the same way, so hopefully you can read that, but if not, just look at the solutions to see them typed in. So for my column for P implies Q, I know that what I'm looking for is a true P and a false Q. It's in other words, true hypothesis, false conclusion. And if that happens, I'll have an F in my implication. So the only time I'm going to see a true hypothesis, a false conclusion, are in rows 3 and 4. I have true, false here for P and Q, and then everything else should be a true. And then for the OR statement, I know that the unusual thing here is for these to be false, so I should look for both pieces being false. That's the only way I'm going to have a false for an OR statement. So P and R both being false is going to happen in the third row from the bottom and in the bottom row. Those are the only two times where I'm seeing false P and false R, and every other place I have a true. And then finally, with my OR statement, with my AND statement, in order for the AND statement to be true, both pieces have to be true. So I'm just going down looking for true, true, and I see it several times here. So in row 1 I have true, true, row 2, row whatever that is, 5, and row 7 all have a true, and everywhere else there's at least one F false. So that'll be my truth table for that compound statement.